Hi everyone, my name is Yihang Yin, master student from Nanyang Technological University. Today I'm going to present BM-NAS, Bilevel Multimodal Neural Architecture Search. This is a framework which makes the architecture of multimodal fusion models fully searchable via a bilevel searching scheme, and it is end-to-end differentiable. We achieved competitive performance with much less search time and fewer model parameters comparing with the current state-of-the-art methods, and our code is now open sourced. So first, let's talk about neural architecture search. The goal is very simple, to find the optimal neural network architecture automatically. And with time going by, there's more and more advanced algorithm for this problem. So at the beginning, we have grid search, random search, and then we have reinforcement learning, evolutional algorithm, or some other kinds of heuristic search algorithms. And then we have Monte Carlo tree search. Later, we have Bayesian optimization or other types of black box optimization algorithm, for example, like sequential model-based optimization. And recently, in 2019, a remarkable efficiency improvement of NAS is achieved by differentiable architecture search, which we call the DARTS. The DARTS framework introduced a continuous relaxation of the neural network architecture, making it possible to search an architecture via gradient-based optimization. So it reduced the search time from thousands of GPU days to just hundreds or maybe even fewer GPU hours. And that's why it's very popular. So we choose to improve it for multimodal problems. And now let's talk about multimodal learning. As we all know that human naturally perceive things in a multimodal way, but for deep neural networks, this need to be broken into parts. So first, we usually need unimodal feature extractors, which we call backbone models. It means for each modality of data, you need to have a separate model to extract features. And then you need a fusion network to join these features and to generate the logics for final classification or other type of task. Usually, there are two types of feature fusion. The feature level fusion, which we call the early fusion, and there is prediction level fusion, which we call the late fusion. From previous work on multimodal learning, we can learn many helpful insights. For example, for architecture design, from CentralNet, we can learn that fuse the intermediate layers of neural networks could be helpful. And now we all know that the attention mechanism has become really popular. So there's multimodal BERT family. It shows that attention mechanism actually works pretty well in many kinds of multimodal tasks. And also there's DFAF. It shows that not only the intermodal fusion, the intramodal fusion could also be helpful. And we also have the AAAI net. It proposed the attention on attention mechanism. And this shows that the stack of attention modules maybe leads to the better performance. And now let's take a look at the original DARTs to see what can be improved for multimodal learning. So the original DARTs only have searchable operation on its edge. This actually means all the searchable operations are unary operations. And the only operation to join to them is summation, which is the blue square here representing the step nodes. But for multimodal features, usually we expect more, right? So, for example, if you want to support the attention mechanism, we need to support the search of binary or even ternary operations on the step nodes. Here, we summarized our contributions. First, towards a more generalized and flexible design of DNNs for multimodal learning, we proposed a new paradigm that employs the NAS to search both the unimodal feature selection strategy and the multimodal fusion strategy. And we present a novel BM-NAS framework to address this problem. And BM-NAS makes the architecture of multimodal fusion models fully searchable via bilevel searching scheme, and it is end-to-end differentiable. And we conducted extensive experiments on three multimodal learning tasks to evaluate the proposed framework. And it shows that both the unimodal feature selection strategy and the multimodal fusion methods are significant to the performance of multimodal DNNs. In this work, we use pre-trained models as feature extractors, namely backbones. We use the output from their intermediate layers of logs for fusion. So in order to freely combine them, we need to reshape all the features to the same shape. And our target shape is a three-dimensional tensor. It has a batch dimension, channel dimension, and length dimension. So for example, if we have five-dimensional video feature tensors, we will apply the pooling operation on the spatial dimension, and we will apply the interpolation on time dimension. And then we will have a 1D convolution on the channel dimension so that we can get a final desired shape. In our BM-NAS framework, we have many elaborately designed primitive operations, especially the binary operations. So the reason why we have this kind of binary operations is that we want to formulate a search space where these operations can be flexibly combined to accommodate various effective future fusion models, such as multi-head attention or the attention on attention. And here we demonstrate a figure to show how these primitive operations can be formulated into this different fusion mechanism by just using two step nodes. And by adding more step nodes, there will be a very large space for the framework to explore better operations. Here we show the structure of our BM-NAS framework. So you can see there is a nested structure. So that's why we named it as bilevel. And the upper level of BM-NAS searches the unimodal feature selection strategy. And it consists of a group of cells. So you can view each cells as a binary operation to combine the feature X and Y. These input features will be chosen from all the raw features from the backbone models or its predecessor cells. But within the cell, we have a lower level, which truly search for the fusion operations. In other words, the combination of primitive operations. And you can see how we assigned weights to edge and step nodes within a cell in the third figure. During the searching stage, BM-NAS will construct a hypernet, or which is a complete graph of all intermediate features, and each edge will be assigned a weight to be optimized. Unimodal feature extractor will be frozen at this stage, and after the searching stage, uh, we will have an optimized weight matrix, and we will sample the weights from this matrix to get the best genotype. The genotype represents the structure of an ideal fusion network. And after constructing the fusion network, we will jointly tune it with our unimodal feature extractor. Here we have a very clear figure to show our datasets and tasks. We perform the multimodal classification task on the multimodal IMDb, NTO RGDB, and the Ego gesture datasets. So the involved modalities are images, text, RGB video, action sequence, depth video, and so on. This is to show that our framework is generalized to many modalities, and of course, our framework can be generalized to other modalities as well. The multimodal IMDb dataset is a multi-label classification dataset. We use image and description to predict the genres of a movie. We adopt the original split of the dataset for the training set, validation set, and the testing set. And we use the max out MLP as the backbone model for the text modality and the VGG transfer as the backbone of the RGB image modality. This is the same setting as a previous state-of-the-art method MFUS. And for our framework, we set the channels to 192, the length to 16, and we will have two cells and one step within each cell. And on the right, we show the best structure searched by our BM-NAS framework, also the comparison of performances with other methods. And since the MMMDB dataset is a multi-label dataset, and the label are distributed very imbalancedly, so we choose to report the weighted F1 score, which takes this situation into account. And we shows the statistic of the label distribution in our supplementary materials. The NTU RGBD dataset is our main task. So this is a very large-scale recognition dataset. It consists over 56,000 samples, and it contains 40 subjects, 80 viewpoints, and 60 classes of daily activities. We will use the skeletons and the RGB videos for the action recognition task. We follow the dataset split of MFUS, so it's actually a cross-subject validation, and here we show how we split the dataset. We use two CNN models, the inflated ResNet 15 models for video modality and the concurrence model for skeleton modality. This is also the same as MFUS. And for our search settings, we set the channels to 128, the length to 8. There will be two cells and two steps within each cell. And on the right, we also show the best structure searched by our BM-NAS framework, along with the comparison of performances with other state-of-the-art methods. The Ego gesture dataset is also a large-scale multimodal gesture recognition dataset. It consists of over 24,000 gesture samples of 83 classes, of 5 subjects, and 6 different scenes. We also followed the original cross-subject split, and we used the ResNext model as the backbone for both RGB and depth video modality. This is the same as 3D CDC, which is a very recent work, also employs the multimodal NAS and the differentiable NAS technique. For our work, we set the channels to 128, the length to 8, and there will be 2 cells and 3 steps within each cell. So on the left, we show our best structure, and on the right, we show the performance comparison. And please notice that as we do not search for the backbone models, so for fair comparison, we only compare with 3D CDC NAS 2, and we share the same settings. And also, in terms of performance, we have superior efficiency, as 3D CDC actually requires 3 groups of backbone models, 3 groups of pre-trained backbone models. And actually, the fusion networks are much more smaller comparing to the backbone models. So as we only requires 1 group of the backbone models, so our framework is actually more efficient comparing with 3D CDC. Besides classification performance, actually the biggest advantage of our work is its superior efficiency. So here we compare the BM-NAS framework with other methods in terms of model size and search cost. As you can see, comparing with MFUS, which is the previously state-of-the-art method, we achieve better performance with only half the model size and more than 10 times faster searching speed. So in a word, BM-NAS is efficient. We also performed an application study on both our search feature selection strategy and the fusion strategy. We do this part by part. So for the feature selection strategy, we will fix our fusion operations and change our selection to random selection over 512s to late fusion, which only select the last layer from each modality. And also we compared with MFUS. And it shows that actually our feature selection strategy is effective. And also for the fusion strategy, we will fix our selection and change the operations within each cell to previously effective benchmark mechanism. For example, like the concatenate and then fully connect layers to multi-head attention, attention on attention, all these mechanism. And it also shows that our fusion strategy is effective. And of course, we have application study over the hyperparameters. Actually, we experimented with a lot of settings and we have many searched architectures. As you can see in this chart, but actually, since this table is too large and there are too many architectures, so I won't go through the details, but you can find it in our supplementary materials. And now let's draw to a conclusion. So in this paper, we have presented a novel multimodal NAS framework, BM-NAS, to learn the architectures of multimodal fusion models via a bilevel searching scheme. And to our best knowledge, BM-NAS is the first NAS framework that supports the search of both the unimodal feature selection and the multimodal fusion strategies for multimodal DNNs. And the experiments we have demonstrated the effectiveness and the efficiency of BM-NAS on various multimodal learning tasks. And finally, we have shared our source code on GitHub, so welcome to use it for future work. And thanks for listening.